Today we're going to look at one of my special functions known as the dilogarithm. So this is a special case of a family of functions called polylogarithms, which are all generalizations of the logarithm. Who would have known? So I made a previous video on this way back when the channel was very young, but I thought I'd do a little bit of an update here. Okay, so let's see what we will take as the definition of the dilogarithm. So we'll say that Li sub 2 of z, in other words, the dilogarithm evaluated at z, where z is a complex number, is defined to be negative the integral from 0 to z of the natural log of 1 minus u over u du. And I say that we are going to take this as the definition because there are a couple of different ways to write down the definition, and I really doubt that this was the first definition. I bet the first definition was the series expansion because, as we'll see, the series expansion is quite nice. And then really this can be thought of as something called the analytic continuation of that series expansion. That's where you take a series that converges only in a certain region and then define a function that's the same as that series in that certain region, but then converges in a much, much larger region, hopefully the whole complex plane. That's something that's done with the famous minus 1 over 12 problem and the Riemann zeta function. Okay, so anyway, let's get to some calculation. We want to do a series expansion for this in the region where the modulus of z is less than or equal to 1. So that's like the unit disk. Okay, so let's start with this numerator, including the minus sign. So I'll take minus natural log of 1 minus u, and observe that I can write that as the antiderivative of 1 over 1 minus u du. That should be pretty clear from derivative-antiderivative rules. And now we're going to do one of our most common tricks, and that is take this rational function, 1 over 1 minus u, and expand it using its geometric series. So let's see. That'll give us the sum, as n goes from 1 up to infinity, of the antiderivative of u to the n minus 1 du. So you might be worried that I immediately changed the bounds of integration, but let's notice that for the region that we are interested in, namely when the modulus of z is less than or equal to 1 over here, this will converge nicely, so we're okay there. You might be a little bit worried about what's going on the boundary, so we'll fudge that, but I think that's okay. So now let's take that antiderivative, and that'll give us the sum, as n goes from 1 up to infinity, of u to the n over n. Okay, so that's looking pretty good so far. And now let's smush that into this over here and see what we get. So Li2z, in other words, the dilogarithm evaluated at z. So now we'll have the integral from 0 to z. We're wrapping this minus sign up in this expansion of natural log of 1 minus u. We have a u in the denominator. Which will descend this power of u back to u to the n minus 1. And then here we've got the sum, as n goes from 1 up to infinity, of u to the n minus 1 over n du. And again, we can exchange the order of summation and integration because the region that we are interested in, the final thing we will have convergence. Okay, so let's see what that leaves us with. That leaves us with this nice object. The sum as n goes from 1 to infinity of z to the n over n squared. Okay, so there we have it. And let's put this over here. So on the unit disk, in other words, the region where the absolute value of z is less than or equal to 1, we have Li2z is equal to the sum, as n goes from 1 up to infinity, of z to the n over n squared. And now this is a perfect place to talk about polylogarithms. So the trilogarithm would have a 3 right there, and then it would have n cubed in the denominator. And in fact, the m logarithm, so Li sub mz, would have an n to the m in the denominator. And I'll let you think about what the Li sub 1z is, maybe post in the comments. But now let's notice immediately from this sum rule, given that, but now let's notice immediately from this sum, but let's notice immediately from this, we have some values of the dilogarithm. For instance, we have the dilogarithm Li2 evaluated at 1 is simply equal to the sum as n goes from 1 to infinity of, well, 1 to the n over n squared. But that's the famous Basel problem. That sums to pi squared over 6. And likewise, we could calculate Li of -1. So let's see what we get that. So Li2 minus 1 will be the sum as n goes from 1 to infinity of -1 to the n over n squared. And I won't work out the calculation for this. I've done it on the channel before, and it's not really the point of this video, but what you land with here is -pi squared over 12. Okay, so next up what I'd like to do is maybe find an imaginary value of this dilogarithm, perhaps the dilogarithm evaluated at I. Okay, so for our other value, like I was alluding to, the dilogarithm evaluated at I. So since I satisfies this rule right here, we can in fact use this series expansion. So here we'll have the sum as n goes from 1 up to infinity of I to the n over n squared. But now, of course, we need to use the fact that I to the 4th power is equal to 1. In fact, we have I to the 0 is the same thing as I to the 4, which is the same thing as I to the 8, which is the same thing as I to the 12, so on and so forth. So I think that's pretty clear. I squared is -1. So if you square I squared, you get I to the 4th on one side and -1 squared on the other side. So that's all going to be equal to 1. And then likewise, if we multiply this whole string of equations by i's, we have I is the same thing as I to the 5th, which is the same thing as I to the 9th, which is the same thing as I to the 13th, so on and so forth. And finally, I squared, which is -1, is the same thing as, well, I squared, which is the same thing as I to the 6, which is I to the 14, and so on and so forth. And then if we multiply that entire equation by I, we'll get -I is I cubed, which is I to the 7, which is I to the 15, and so on and so forth. So the important thing here is that I to the 4 times n is equal to 1. I to the 4 times n plus 1 is equal to I to the 4n plus 2 is equal to -1, and finally I to the 4n plus 3 is equal to -I. So that motivates us to split this into all of those pieces. That's exactly what we're going to do. So this is going to start with the sum as n goes from 1 to infinity of 1 over 4n squared. So that's where we're putting I to the 4n in the numerator. And then for our next term, we'll have plus I times the sum as n goes from 0 to infinity of 1 over 4n plus 1 squared. Here we have to go 0 to infinity just because of how we're indexing this right here. So that's attached to, of course, the I to the 4n plus 1 term in the numerator. I just pulled it out. Now let's look at I to the 4n plus 2, which will give us a -1. I'm actually going to put it right on top of this. So here we can subtract these, and we'll have the sum as n goes from 0 up to infinity of 1 over 4n plus 2 squared. And then likewise, we'll have a -I for this next bit. This will be the sum as n goes from 0 up to infinity of 1 over 4n plus 3 quantity squared, like that. Great. Now what I'd like to do is push these two together and then factor a 2 squared out of the denominator. So let's see what that'll leave us with. 2 squared is obviously 4, so we're factoring a 1 over 4 out. And then I'll put this in green parentheses so we can see where it comes from. So this will be the sum as n goes from 1 up to infinity of, let's see, 1 over 2 times n squared. Again, we only factored a single 2 out of there, but we had to square it. And then from that, we will subtract the sum as n goes from 0 up to infinity of 1 over 2n plus 1 squared. So this is what we get from that other green underlined term. Now we're going to play the same game on these two underlines. So I'm going to pull an I out of the whole thing, and then we'll just put them next to each other. There's not anything we can factor out of them though, because they're both odd. So that's going to give us the sum as n goes from 0 to infinity of 1 over 4n plus 1 squared minus the sum as n goes from 0 to infinity of 1 over 4n plus 3 all squared. So something like that. And now here's where the trick comes in. We're going to push these together and turn them into alternating sums. So here, this is a reciprocal of all of the even squares. This is a reciprocal of all of the odd squares. So the odd squares in this case are connected to a minus sign, whereas the even squares were connected to a plus sign. So that means we can simply write that as an alternating series. Now we have the sum as n goes from 1 to infinity minus 1 to the n over n squared. So just to continue our underlining, that's what we end up with putting those two green parentheses together. And then we'll do the same thing over here. This makes up all types of odd numbers. Odd numbers are either 4n plus 1 or 4n plus 3. But it's going to alternate. So we can encode that with some alternating stuff as well. So I'm going to write this as plus I. And now we'll have the sum as n goes from 0 up to infinity of minus 1 to the n over 2n plus 1 quantity squared. And then let's underline that with the same color codings just so that we have it. Okay, now, well, look, this is exactly what we had before. This was the dilogarithm at minus 1, which we said was minus pi squared over 12, combined together with this minus quarter, gives us minus pi squared over 48, plus I times that sum. But that sum is actually a constant in its own right. It's called Catalan's constant. There are a couple of different letters that are used for it. You know, I've seen G pretty often. So let's say this is Catalan's constant. So now we could potentially just add this to our list of values that we are compiling over here. So now we have Li2 evaluated at I is minus pi squared over 48 plus I times Catalan's constant. Okay, good. Now let's look at something else. And all of those can be achieved via functional equations that the dilogarithm satisfies. So we're going to finish things up by looking at a certain functional equation that's satisfied by the dilogarithm and use it to find one more value. And I think we'll probably do another video on this later. Okay, so here's the functional identity which we'll show. So here we've got Li2z plus Li2 minus z is in fact equal to pi squared over 6 minus the natural log of z times the natural log of 1 minus z. Okay, so I think that's pretty cool. It makes this combination of dilogarithms, well, equal to a constant. And then, well, some function that's more elementary. It's the logarithm function. Okay, so what's our strategy here? Well, we're going to show that a combination of the left and the right-hand side satisfy an interesting differential equation. What I'll do is set f of z equal to Li2z plus Li2 minus z, and then plus the natural log of z times the natural log of 1 minus z. Okay, great. So if this functional equation holds, then that means f of z should indeed be a constant function, and, well, it should be equal to pi squared over 6. So since we're thinking that f of z should be a constant function, probably its derivative should be 0. And I don't really mean probably, I mean definitely its derivative should be 0. The only thing that has 0 derivative everywhere is a constant function. Okay, so let's get to it. So here, we're going to need to take the derivative with respect to z of Li2z. So Li2z is this. I'm going to take a minus sign out front, and then we have the integral from 0 to z of the natural log of 1 minus u over u du. Then we need to take the derivative of this. Again, I'll take my minus sign out front. Derivative with respect to z. Now we have the integral from 0 to 1 minus z of, let's see, same thing, natural log of 1 minus u over u du. Great. And now I think we can just take the derivative of those. That's pretty easy with the product rule. So that's going to start off giving us plus natural log of 1 minus z over z from taking the derivative of the first term. And then we'll have minus natural log of z over 1 minus z from taking the derivative of the second term, being careful to use the chain rule there. Okay, so now let's take these derivatives, keeping in mind that we have to use the fundamental theorem of calculus part 2. So let's see, bringing this minus sign down, and then the derivative with respect to z, well, in this case, all we have to do is plug a z right into our integrand. So we have natural log of 1 minus z over z. Then we'll do the same thing here, except we plug 1 minus z into the integrand, and then multiply by the derivative of 1 minus z, again because of the chain rule. But the derivative of 1 minus z, well, that's exactly equal to minus 1, so that's going to cancel this. So here we're going to be left with natural log of, well, 1 minus z, which is in fact just equal to z, over 1 minus z, and then we just bring this stuff over. Natural log of 1 minus z over z minus natural log of z over 1 minus z. Okay, good. But let's check it out. Some stuff cancels. In fact, this term will cancel with this term, and likewise, this term will cancel with this term. So that tells us what? That tells us that f prime of z is equal to 0 everywhere, but in turn, that means that f of z is equal to a constant. But which constant? Well, we can just evaluate this function anywhere, and we'll get that constant. Well, we'd probably like to evaluate it somewhere that makes sense, like, in other words, somewhere that's easy to calculate. So let's do it at 1. So this is equal to f of 1. So let's see, that's going to give us Li2 of 1 from this right here, plus Li2 evaluated at, well, 1 minus 1, which is 0. And then we'll have, let's see, it's right here. So this will be the natural log of 1, which is 0, and then the natural log of 1 minus 1, which is the natural log of 0, which is not defined. So how would we take that definition? I think the best way to do it is via a limit. So let's take the limit as z goes to 1 of the natural log of z times the natural log of 1 minus z. So something like that. But then the dilogarithm evaluated at 0, it's pretty clearly 0 by this definition or by this definition. So that means this trudges off towards 0. And then the dilogarithm evaluated at 1 is simply pi squared over 6 by our previous observation. So we have this as f of z equals pi squared over 6. And then all that's left is this limit over here. But now that I look at that, I think if you've gotten this far into the video, it's pretty easy for you to show that that limit is indeed equal to 0. So that means we have f of z is a constant. It's pi squared over 6, but rearranging f of z equals pi squared over 6, we'll get this right here. Okay, so let's use this functional identity to get one more value of the dilogarithm function. Okay, so like I said, now we're going to look at an application of this formula, this functional equation that we just derived. And this is most definitely the simplest application. We want to look for the place where z and 1 minus z are the same. Well, that'll make it super easy because that means this left-hand side will collapse just to one thing. So, like I said, we need z to be equal to 1 minus z. Oh, but that means that 2z is equal to 1, which means that z is equal to 1/2. And I mean, it was probably pretty silly to do that because we did a much larger calculation just a second ago. Okay, so plugging z equals 1/2 in here, we'll see that 2 Li2 evaluated at 1/2 is equal to, well, pi squared over 6 minus the natural log of 1/2, Well, times the natural log of 1/2. So that's minus the natural log of 1/2 squared. But that's actually all squared. Now we're going to use the fact that the natural log of 1/2 is minus natural log of 2, but squaring it makes that minus sign disappear. So that means this can be brought down to something maybe even a little bit nicer. Pi squared over 6, and then we'll have minus the natural log of 2 squared. But we have this 2 here. So let's divide both sides by 2. That's going to give us a 12 right here. And then we'll have a minus half out front. And then finally, I want to finish this up with one other thing, and that is to use the series definition of the dilogarithm. Well, if z is equal to half, we're well within the region of convergence. So that'll give us the sum, as n goes from 1 up to infinity, of 1 over 2 to the n times n squared. So there we have it. This is a nice sum, which looks pretty innocuous, but as you see, we used some fancy tools to get at it, and that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.